Welcome to this video lecture on binary logistic regression and partial least squares regression. We'll begin with binary logistic regression. As the word binary suggests, binary logistic regression deals with a regression model where there are just two possible outcomes for the response variable. So it's a yes-no outcome. So instead of the outcome being normally distributed response, instead it's a yes-no response. It's either a yes or no. An example of this would be an applicant who applies for credit on their credit card. Will they meet those payments or will they default on the payments? And of course, that's a question that's of interest for the credit card issuer. And it's a question that they would like to be able to estimate the answer to before issuing the card to the applicant. And so a model that's used to make that prediction is called a credit scorecard. And we can use binary logistic regression to perform this task. So the response is whether the client will default on the credit card balance, on the credit card loan. So default, yes or no. Predictors that could be used would be the time the applicant has been at their current address and the time the applicant has been in their current job. And when we do the analysis with some existing data for clients for whom the data and the outcome is known, we can get an analysis of variance table like this. Notice that the overall p-value for the regression is less than 5%, indicating that this model is a useful model for making a prediction about default. And in particular, the variable months in job is a useful predictor. We can assert that in particular about that variable in the model. The number of months that the applicant has been in their current job is useful for predicting whether or not they may default on their credit card loan. When we look at the coefficients, we notice that the coefficient of months in job is negative. This means that every extra month the applicant has been in their current job makes them less likely to default on their credit card loan. We can estimate the odds ratios for these predictors. The odds ratio for months in job is 0.9492. This tells us that for every extra month that an applicant has been in their current job, the estimated odds of a default reduces to 0.9492 of its previous value. And we have a confidence interval for that value as well. You might notice that the confidence interval for the months at the address includes the value 1, which would represent no change in the odds ratio. And that, of course, is consistent with the p-value for that variable earlier, which was seen not to be significant. We can supply values then for a new applicant. Here we have an applicant with 29 months at their current address and 18 months in their current job. And an applicant like that has a high probability of defaulting on their loans. The probability is estimated at just over 80%. So that's using binary logistic regression to predict a yes-no outcome, as opposed to our usual use of regression, which has been to predict a continuous response variable. Here the response is a yes-no outcome, a 1-0 outcome. We now move on to partial least squares regression. A problem arises in regression if we have more variables than we have observations. Consider a very trivial case. Let's say we have a scatter plot in a simple regression analysis of a variable y and a variable x, but there's only one observation. So on the graph, there's just a single point. Of course, it's impossible to draw the best fitting line through one point. One point just does not provide enough information to estimate the two parameters that need to be estimated, the intercept and the slope. So in that trivial case, it's obvious that having more predictor variables than observations is just a problem. We need more observations than that. Now, we can address this when we have a multiple regression model, but we have more predictor variables than observations. We need to somehow either get more observations or reduce the number of predictor variables. And we can reduce the number of predictor variables by using partial least squares regression. To take an everyday example, body mass index can be used to predict some health outcomes. Now, body mass index is based on the weight and the height of the individual. But what it does, it takes the weight and the height and combines those into a single measure called BMI, body mass index, which is better at explaining health outcomes and which is simpler because it's a single predictor. Now, it's not a linear predictor, but nevertheless, it illustrates what we're doing here. It's not a linear combination. So in partial least squares regression, we perform a similar task. We take the predictor variables that are available and we reduce them to a smaller number of predictor variables. And these are called latent variables, variables that are hidden inside the more obviously available variables. So this is properly called projection to latent structures, but it's commonly referred to as partial least squares regression. So it reduces the number of variables so that we can proceed with a regression analysis. And it does that by extracting the information out of the available variables. There's a second advantage of partial least squares regression in that the latent variables are not correlated with each other. So if we had a problem of multicollinearity to begin with, where the available predictor variables have some correlation with each other, using partial least squares regression addresses that problem as well because the new variables will not be correlated. So here we have an example where a sports scientist wants to explore what it is that would predict the energy expenditure of an athlete. There are 9 observations, so observations on 9 different athletes, but there are 17 different variables like the athlete's age and body mass index and weight and body fat and heart rate and so on and so on. So we have many, many variables, but only 9 observations. So we use a partial least squares regression to explore this relationship. And some of the output is shown here, and you'll see that 5 components have been selected out by using the original set of 17 variables. The p-value in the ANOVA table shows us that the selected model is significant. And here we see that the selected model is the one with the highest R-squared predicted value at 61.3%. R-squared predicted there in the final column. The R-squared predicted is better than R-squared adjusted for measuring how useful a model is to make predictions. And the way it works is the R-squared predicted is calculated by omitting the observations one at a time from the data set. And then the model obtained each time is used to predict the missing observation. And then a cross-validation is carried out using the PRESS statistic, the predicted residual error sum of squares. So it establishes that the model is useful as a predictive model. And this selected model explains 92.1% of the variance in the predictors, as shown there in the second column. So now we have a model that we can use for making predictions. So we can supply some values for a new athlete. The values of the individual measurements are not shown here, but when we provide those values to the software, it calculates a fitted value. So 3613 is the predicted energy expenditure for an athlete having those attributes that we have supplied to the software. There's also a confidence interval shown, which would be the estimated average energy expenditure of athletes like that, and a prediction interval, the energy expenditure of an individual athlete like that. You can read more about this in the textbook in section 6E.